Okay. Hi, everybody. Sorry for the technical issues. I'm Eyal, and I'm going to present an IDA plugin that I wrote called Karta. But let's start from the beginning. I'm Eyal Itkin. I'm a vulnerability researcher at Checkpoint Research. Usually, my research projects are focused on embedded devices and network protocols, which was the background for this specific IDA plugin. Usually, you can see my research projects or suggest your own projects through my Twitter. And let's begin. The motivation for the research for this plugin was that usually malware researchers or vulnerability researchers in firmware projects need to identify open source versions inside a given binary. This could be the version of OpenSSL that is being used, and libpng, zili, but you'll see often. And you want to identify the open source for specific reasons. Sometimes you want to help researchers in the reverse engineering process because I want to find out what the binary does and does it support TIFF if it has libTIFF inside it. Locating one-days in given firmware. In many firmware projects, you don't need to find a zero-day because they don't update their open sources. So you must probably have a given one day that is exploitable, but you need to find out which open sources are being used, statically linked inside the firmware, and what are the versions of each open source. And hopefully we could do that automatically. We want to identify libc functions because we don't have good heuristics to find strlen or memcopy, strncopy, or a socket when you reverse engineer a firmware file. On Windows, you will have it for libc, but if you have an embedded file, it's an HP printer for some reason, it's on ARM CPU, you need to find it all on your own. And one more reason that several people here in the audience know that because I worked with them on a given project is that I worked 3 days to reverse engineer a specific SNMP model in some device, and after which I found out that it's a used open source called NetSNMP, and I knew the open source already, and I simply couldn't realize that I'm reversing a known open source. So I don't want to reverse engineer NetSNMP over and over and over again. If we would have an automatic tool to identify it and match the functions, I could skip directly to interesting models instead of reverse engineering the same open source that is already known and has no good exploitable vulnerabilities. The problem with current tools is that usually the firmware is huge. We have a specific firmware we used in a previous research project, which has roughly 65,000 functions. In Cisco routers, you have hundreds of thousands of functions. And even on TeamViewer, which is a simple process on your Windows computer, you have roughly 150,000 functions. Binaries are pretty large, and we need to cope with that and find our functions inside these large binaries. And this is the problem, because most bin diffing tools are dependent on the size of your binary and not on the size of the file or open source you want to match inside it. So if the library size is K, most of the tools are dependent on N and not on K, which means that although bindiff and diaphora are really good tools for binary diffing or patch diffing, they fail poorly on huge embedded files, firmware files. They simply can't find small known chunks inside a big library. When I used diaphora in one project, the DB rose to roughly 3 gigabytes, and then the program crashed. And when I used bindiff, it took it 3 hours, and it found nothing. We want something that takes into attention the size of the firmware and the size of the library we want to find. And hopefully, the complexity will be dependent on K rather than on N. Some background. Last year, we had a research on the fax protocol. Here's the link for the full research. The firmware for our test case was an HP OfficeJet, a simple common HP OfficeJet. And the purpose of the research was to find a remote code execution over the fax protocol, which worked. Now we want to look on this project and see how that plugin, Karta, would help us. In our research, we wanted to find develop a debugger. And we could debug for any one day we found in the firmware for the web interface, for example. Exploit one day, use a debugger, and then debug the fax protocol. In order to look for one day, we need to identify the open sources. We need to find the vulnerable functions. And eventually, we used Devil's Ivory from GSOAP, which is not the important part. The bad part for us was manually identifying the open sources and manually identifying the vulnerable functions. If we would have used Karta, for instance, we can see that the basic output, where once you execute the script, is this nice list, which shows you that the open sources that are used are libpng, zlib, OpenSSL, and a vulnerable version of GSOAP. Because if you simply type in Google GSOAP and vulnerabilities, you'll find that this specific version is vulnerable to Devil's Ivy. And now the most important part is, would Karta match the function and simply tell us, here is the vulnerable function, start the exploit from this point. So let's see. And yes, simply out of the box, you take a firmware, you find out the vulnerable open sources which are embedded inside it, match the configurations to find a function, and that's it. And in an additional research, this time from Project Zero, they have a series of blog posts about WebRTC in this link. And they found one specific CVE, which is not in Chrome itself, but in a library called libvpx. And they specifically said that this vulnerability is most probably affects more versions and more products. Okay, let's take TeamViewer, for example. Execute Karta and check if it's vulnerable to the same vulnerability which Google found. And we found a vulnerable version of libvpx, actually a really vulnerable version because it's outdated in 2 years. This is the code function of the vulnerability, and pay special attention to the numerical constants inside it, because when we executed Karta, we found it in IDA, and we can see the same numerical constants, and it took it roughly 10 seconds to find it. So the tool works. It's already on our GitHub account. Now let's check out how it works. Okay, we want to map the binary, and actually really descriptive mapping of the functions in the binary. We are interested in a specific open source, which is found over there. And it should be somewhere inside a large firmware file, a large executable. And we're not interested in all of the executable. We only want to find the open source. If we zoom in and we pay special attention to each of the functions in the selected area, we will see that the selected area starts with all of the functions from one specific compiled source file, followed by all of the functions from an additional compiled source file, and so on and so forth. We can see that essentially the compiler compiled each file independently and then linked them all together, which means that instead of matching each function on its own, we can use this behavior in order to match full files one to another instead of matching single functions. And that's the basic idea behind Karta. We want to map the files inside the binary address space. This is the plugin. It's already on our GitHub account. And we are focused on binary matching and not binary diffing. The matching is done on a geographical base, which means we want to locate the binary. We want to locate the open source and then locate each file inside it. And one important feature of our plugin is that it's architecture agnostic. We compile the configuration for libpng, for example, on x86, and then matched it on an ARM big Endian 32 bits. You simply need to compile the configuration once and use it everywhere. Now let's see how it works. The first stage is fingerprinting the open sources which are used inside a binary. It's an independent stage. It doesn't have anything in common with the matching phase, so we can simply fingerprinting and that's it. We want to find which versions are used, which open sources exist, and hopefully we'll get a specific version. It works with, for now, it works with a basic string search. And you can say, okay, you simply search for given strings. Why would that suffice to find libpng or zlib or netsnp? And it turns out it's good enough, because if you look at this string, descriptive string from libpng, there's no reason that the credit for the developer will be in a string inside the binary. Usually it's comments in the open source, but he decided to compile it in instead. We should, in the future, improve this thing to search for constants or anything other than basic strings. But even if we look on a common OpenSSL, we can even see that it's an OpenSSL, the specific version, the specific model, and even the compilation date for the open source in the string, inside the binary. It turns out that in most open sources that we looked that are popular in embedded devices, you have such descriptive strings compiled inside it. Basic string search is enough for the beginning. Now that we know that it uses libpng or OpenSSL, it's time to match the specific version inside our binary. Sorry. Okay, we want to locate what we call anchor functions, which are strong descriptive functions that we won't easily be confused with functions from other projects or other open sources, which means that they should have quite unique artifacts. These could be unique numerical constants, such as these constants from SHA-2, I think. And it could be some really long string from this version of libpng. If you have this string inside your firmware, it most probably holds libpng. And if one function refers to this string, you will know what this function is. This means that using unique enough constants, we can search throughout the entire binary for anchor functions. And once we found a single function, we can zoom in, because we know that the open source will be compiled to this specific area, and it will look like this. We will have k-1 functions potentially before this match, and k-1 functions potentially after this match. But the entire open source will be compiled into this specific area, and it won't be scattered around the firmware address space in other ways. Once we find the first anchor, we have many more. In libpng, we have roughly 50. We found all of the anchor functions. We have matches to begin with. Now for the next phase. Next phase, okay. Now we can draw basic file boundaries around these matches, exactly like we did when we zoomed in on the library itself. If we know that a function is contained in a file with 5 functions, and we already found one, we have basic boundaries around it. And we can do the same all over again. And sometimes 2 files will be adjacent enough to border each other. So we'll have a better limit than simply saying, okay, we have a given set of functions that could be beneath us, because we have a lower bound from the upper bound of a given file before us. Now we have basic file boundaries. Essentially, we know where several files could reside. Some of the files will be floating. We don't know where the files could be inside this scoped area. We refer to them as omnipresent. They could be anywhere. When we'll find a single match from that file, we'll pinpoint its location. Only now, when we have this specific scope, we can start building a canonical representation for each function. We want to know the size of the function, the size of the storage stack, the numerical strings, numerical constants, the strings, call graph, everything we need to know about each function. But we only need to do it for order of magnitude of k functions instead of n, meaning that for libpng, we need to do it for roughly 400 functions instead of 100,000 functions. Once we build each canonical representation, we can refer to that function later on, and it will look like this. We know what is the frame size, numerical constants, which functions are being called, and from this point onwards, we will only work on this canonical representation of each function. We don't need IDA anymore. This means, too, that if you implement the basic preprocessing phase for your reverse engineering tool, for example, Radar2, you only need to implement this part. The rest of the logic is completely disassembly independent. It only needs these representations. Now we need to look for file hints. You find it in Microsoft binaries, in many embedded devices. You have trace strings from traces from log outputs, which often contains the name of the file. So it will be tcp.c or rdp something.c. And this means that there are some functions which contain the name of the file inside them. If you already know where the file should be, we could look inside it and search for these references and find more matches, and sometimes we can find in our scoped area more files. This gives more information. And inside each file we have agents. It's like anchors but weaker. They have locally unique numerical constants or locally unique strings. And we can find them with a high true positive probability, which means that the chances for error are slim. In libpng, on the office digit case, at this phase we had roughly 70 functions that were already matched, even before we tried the traditional matching of scoring similarities, call graph, and every other heuristics, which is the last phase. Here you do everything you do on every other tool, bin diffing tool, bin matching tool. You work on, you score each feature, you check what feature match, what features don't match, and you have a basic scoring function to declare if the functions are similar enough to be declared as matches. This part is generic. You can simply take it from your tool, plug it in, and it will work. The most important part is the geographic location, because we have additional scoring we could use, and we have penalties we could infer also. Geographic matching means we have several assumptions, which are hard rules we must obey. This means that a candidate for a given file must reside on the scoped area of that file. If you know that SHA-1 init should be in SHA-1.c, there's no reason to look for it on the file md5.c or aes.c or any other file. If you already know that SHA-1.c has 4 candidates and we don't know which candidate is which function, we only need to look for these 4 matches and that's it. So we have a low address space to look for, meaning that it will be much faster and the probability for error is slim. In addition, most of the compilers tend to preserve the function order, which means that if I found SHA-1.init, the next function will most probably be SHA-1.digest and then SHA-1.finalize, because that's the order of the functions inside SHA-1.c. Karta gradually learns if the compiler preserves the order or not, and then adaptively boosts it. This gives a distinctive amount of matches with high probability if Karta found the compiler to preserve the order. And working on the neighbors of each function, we could say that, okay, we had a free streak of a function from the file matched to a given binary. The next function matched to the next function in the binary, and so on. And we can even guess that, okay, maybe even the next function will match, and check. And if the score will be big enough, we'll match it. That's how Karta is working. Now, how do we use it? Karta compiles configurations from the open source because it's source code assisted binary matching. This means that you simply take your favorite open source, you compile it in debug mode, so you won't have compiler optimizations. You compile a source, you get the binaries, and Karta is being trained on these O files to produce a JSON configuration. You could later on read the configuration. We have several precompiled configurations on a GitHub. Now when you have a given set of configurations, the first phase will be identifying the used open sources. Once we identify the given specific version and we have a configuration for it, we'll take the binary, we'll match it to the specific configuration, and now the matcher will take the binary, the configurations, and we'll try to match it. As simply as that. And hopefully it will find most of the functions inside the binary. And we'll have an annotated binary to start a research instead of reverse engineering the same functions all over and over again. Thumbs up. Okay, this is a new part we added today. It's on our GitHub account, or it should be on our GitHub account now. When working on x86 binaries, IDA does a pretty good job. When working on firmware files, for example, ARM files from our research projects, IDA could be improved. It fails to find transitions between ARM and thumb code sections. It fails to find many functions. We need to improve the analysis so Karta could be used. And instead of manually identifying where a function starts and where a function ends, which could be pretty meticulous, I developed an additional part to be used with Karta, which uses really basic machine learning in order to improve the analysis of IDA. It's being trained on your own IDB, and then it improves the same IDB from the same file. You could already find it on a GitHub account, and this is the blog post for this research published right now. Thumbs up should be used as a pre-processing phase before using Karta. We checked it on several firmware files, and we actually used it on a MIPS binary and MIPS ELF file before we started our current research project. And for the HP OfficeJet, it took 40,000 functions into 70,000 functions. And on the MIPS file, it took 200,000 functions into 50% more, I think. It works quite well for us. Maybe it will work also for you. And now for the results. We tested the main matching results after we manually analyzed libpng, zlib, and OpenSSL. We have several disclaimers because OpenSSL is huge. It has 5,000 functions. Only 3,500 functions were compiled inside the OfficeJet. And I had to manually analyze each of the functions because that's how you test it. Eventually, in libpng, we had 300 functions. We found all of them. We found all of the Xref functions that are inside the HP OfficeJet firmware. We had no false positives, and it took less than 30 seconds to find all of libpng inside a huge binary. For zlib, it was even easier because it took roughly 20 seconds and no false positives. And even in OpenSSL, it takes less than 20 minutes to find the vast majority of functions inside OpenSSL with 8 false positives out of almost 3K functions. So in this test case, it worked quite well. Later on, we tested it on Windows binaries, on other binaries, and it seems to be consistent. The results are when I executed Karta on a VM on my laptop, and these are the timings. So it's not the best timing constraints. It probably could be faster on your computer, but it's fast enough. Even on OpenSSL, you can execute it, go to eat something, and way before you get back, it's finished. On libpng, libvpx, zlib, it simply finishes fast, and that's it. Why use Karta? There are many good open source and closed source tools that could be used for binary matching or binary diffing. You have function sim search of Google, Diaphora and Pigaios from Hoshan. You have BinDiff, you have a new version of BinDiff just came out. Every program here is good, but each program should be judged against the goal of the developer of the program. Because if you read the documentation of BinDiff, BinDiff was being developed for patch diffing, for finding similarities in different close enough binaries. It wasn't designed to match open sources in a huge database of a firmware file. Pigaios is the same. Diaphora is the same. Pigaios is more matching oriented. Eventually, you could use BinDiff, but it wasn't designed for binary matching. And it's really great for patch diffing, so use it for patch diffing instead. If we compare the basic tools in our specific scenario of matching open source functions, we can see this basic table. And essentially, there's no other tool that is architecture agnostic that works quite well on large enough binaries and that is aimed upon matching the functions. It's hard to match the functions and be architecture agnostic when you use fuzzy hashing, like in function sim search. And you can't use all of the features from the open source when you try to match, because Pigaios tries to compile the sources on its own, and finding out macros and structs will differ from each execution. If you simply compile it with a regular compiler, you don't have to emulate a compiler to derive the features. Each tool here is good. Most of them were designed for binary matching. They were designed for patch diffing, and they work well for patch diffing. That's it. This is the tool. Thank you for coming.
Thank you, Eyal. That was great. Thank you so much. High five. First BSidesTLV talk ever for you, and hopefully more soon. Remember, if you want to be a speaker at BSidesTLV, you have to submit a talk in our call for papers.
Questions?
What's that?
Questions?
We have time for one question. We have time for one question for Eyal.
Yes.
Please, repeat the question.
When you tested Karta, one of the surfaces is using anchors in order to locate the function inside the big binary. How sensitive is it to different compilers?
Okay, so the question was, the first stage was anchor functions, and is it sensitive for different compilations and different compilers? Anchor matching uses a high enough entropy of numerical constants or long enough strings, and the compilation doesn't change that. So we only need to scan IDA to search for strings or numerical constants. The compilation doesn't change that. If you compile your own configuration without optimizations, you will know which constants are connected to which functions. And on the binary itself that you look for, the compilation doesn't change that at all. So the anchors are quite stable, hence the name. And in libpng, we had roughly 50 anchors, and it finds most of them. Just before I finish, we have a booth outside. If you wish to work on such projects in our research group, we have a course for new employees and current employees called CSA, and you could visit us in the booth.
In the chill out zone.
In the chill out zone.